Teleportation is real. Not the kind you've seen in movies, not beaming people across the galaxy, but in December 2025, scientists did something that was considered physically impossible just a decade ago. They teleported a particle of light across 270 meters of open air between two completely separate devices, and it worked with 82% accuracy. This isn't science fiction. This is the beginning of the quantum internet. Let's start simple, because the word teleportation carries a lot of baggage. In physics, teleportation doesn't mean moving an object from one place to another. No matter is transported. Nothing physically travels. What gets teleported is information. The quantum state of a particle, its properties, its identity, is transferred to another particle somewhere else. Think of it this way. Imagine you have a coin. Instead of mailing the coin to someone, you somehow make another coin on the other side of the world, perfectly identical, in exactly the same state, without ever physically sending anything. That's quantum teleportation. The key is something called quantum entanglement. Two particles can be linked in such a way that measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance. He didn't believe it was real. He was wrong. But here's the problem scientists have been fighting for decades. To teleport quantum information, you need a source that produces entangled photons reliably and on demand. And you need two separate sources to produce photons that are identical enough to interfere with each other. That second part, two independent sources producing identical photons, was considered nearly impossible. Until now. Quantum teleportation was first demonstrated in 1997. Back then, scientists managed to teleport the quantum state of a single photon, a huge achievement, but done under controlled laboratory conditions with identical sources over almost no distance. Over the following years, the distances grew, first centimeters, then meters, then kilometers, but only through optical fiber, where conditions can be perfectly controlled. The real challenge was always this: can you do it in open air, between completely independent devices, without any physical connection? Because that's what a real quantum network needs. Not a lab, not a controlled environment. Buildings, cities, the real world. Two teams began working on exactly this problem, one at Paderborn University in Germany, one at Sapienza University in Rome. They spent a decade engineering something that had never existed before: two separate quantum dots, tiny semiconductor structures that emit single photons, that could be made to produce photons identical enough to interfere with each other. This required controlling the color, the timing, and the quantum properties of each photon with extraordinary precision. It took 10 years, and then they were ready. The experiment took place across the campus of Sapienza University in Rome. 3 laboratories, 2 buildings, connected by a 270-meter free space optical link, meaning the quantum information traveled through open air, not through any physical cable. Here's what they did, explained simply. The first quantum dot produced a pair of entangled photons. One stayed in the lab, one was sent through the air to the second building, 270 meters away. Meanwhile, a second quantum dot produced a separate photon, the one whose state would be teleported. These 2 photons, from completely different, independent sources, were made to interfere at a beam splitter. A measurement was made, and the result of that measurement was used to instantly recreate the original quantum state at the receiving end. The teleportation fidelity, 82%, well above the classical threshold of 33%, the point below which no quantum advantage exists. What makes this different from everything before is this: the 2 sources were not identical. They were different quantum dots with different physical properties, engineered to be similar enough through external controls. That is the breakthrough. Not just teleportation. Teleportation between independent, dissimilar devices. The kind of devices that would actually exist in a real quantum network. Professor Klaus Jones from Paderborn University said the combination of material science, nanofabrication, and quantum technology was the key, and that 10 years of strategic planning had finally paid off. The quantum internet just got one step closer. Here's what I keep coming back to. We use the word teleportation so casually, in movies, in games, in everyday conversation, that we've almost forgotten what it would mean if it were actually real. It is real. Not for people, not yet, maybe never in that sense, but for information, for the quantum states that carry the deepest properties of matter. Teleportation is no longer a concept. It's a result. Published in Nature Communications, replicated, verified. A quantum internet built on this technology would be fundamentally unhackable. Any attempt to intercept the signal would destroy the quantum state, making the interception instantly visible. That's not encryption, that's physics. And it started with 2 quantum dots, 2 university buildings, and 270 meters of open air. Science doesn't always arrive with headlines. Sometimes it arrives quietly, in a laboratory, after 10 years of work, and changes everything. Stay curious.